In the last segment, which was a bit longer, we were discussing about how to draw shear force and bending moment diagram in a systematic way. But then sometimes it's a bit cumbersome, and you won't feel like doing the way we discussed there. So then there is another information or concept which, if you know, you can reduce the work that you have done in the previous segment quite a bit. That is one. Or else, even if you have done that, you can check quickly by the concept which we are going to discuss now, and that is about, there is a relationship between the load which you are applying, the shear force as a function of those loads, and the bending moment that gets developed. So that is the concept which we are going to discuss in this segment. There is the relationship between shear force, bending moment, and the load. Okay. Now for that, suppose you have, there is a beam like that, and you have, say, a load condition. So I am just taking a continuous load of arbitrary shape to tell that it's of any nature. And then to derive that relationship, what we do is, let's say we will pick a segment of length delta x at a distance of x from the beginning, from the origin. Okay. And then suppose this weight distribution has a function of w as a function of x. Okay. And obviously that is in a Newton per meter or similar thing, a density, a linear density. Then what you can do is, you can draw the free body diagram of this small segment. Let me draw this. So in a bigger form, I am drawing this. Okay. And now on that you will have to show the shear force and bending moments like this. So the shear force, positive senses are this. Let me take a moment to, in fact, draw the convention on such a segment, okay, of positive shear force and bending moments. Let's see. If you have, if you have a particular segment like that, okay, then the shear force, positive values are considered like this, and the moments, positive moments are like this. And I will write here inside this, these are all positive. So this is a convention. Okay. So there is nothing wrong or right about this. This is right because people have taken this to be a convention. Okay. This is a bit, see, for me, it's this side, this V is a bit non-intuitive in a sense, so what it tells you is, suppose there is a beam like this. Now the positive sense of shear force is telling you that the beam, when slides like this at a particular location in shear, if it fails like this, so that is considered positive. That means this side you have pushed it so hard that this segment, so now you see here, this right hand side is applying a force of, say, this type, right, on the left side. And similarly, if you see from the perspective of right side portion, the left one is applying a force like this, right. So that these are the forces which have been taken as positive. Okay, and similarly, if you think about the moments, the moment which turns the beam like this, concave upward, so that's considered positive. So that's the whole thing. Okay. So these are the positive sense of, and then this picture you should always keep in mind. Now this square tells you that this is a segment, and this side thing conveys that if you keep the left side portion, what are the positive senses of V and M, and this side tells you that if you keep the right side portion in the FBD, what are the positive sense of V and M. So that's the whole convention thing. Okay, and let me keep this thing a bit to the left here. Yeah, maybe here. Okay, done. Now coming back to here, so now because loads are coming here, so your V, if it is V here, then in the positive direction we will consider that a increase in V has happened, V plus dV, and similarly if the moment is M here, here the moment has become M plus delta M. Okay. Now if that's the thing, because here, you know, this in this small segment you can think of this omega W to be constant in a way. Okay, it is dx is so small that you can think of this as constant. So W delta x is the total load which is acting, and this is in a way, you know, what do I call, you can equivalently it gets applied at this. Okay, while calculating the moment, this is the easier way to calculate that. Okay, let's see. First let's balance the shear forces, the force balance. It will give you what, say this is upward is positive, say V, I'll use this, so now, yeah, so V minus V plus delta V, and force wise what's coming, so now this minus W dx, right, delta x is 0. So that's the force balance equation for this particular segment. Now that gives you what, V cancels out, you have negative of delta V, which is your W delta x, implies your delta V over delta x is like negative of W, and in the limit we are seeing everything in the limit when delta x tends to 0. So in the limit that delta x tends to 0, you have dV over dx is negative of the weight, and then weight at that location, so I can also write that it's a function of x, it's a function of x, and that's the relationship. Okay, and if that is so, you can always write, you know, like this. So V between 2 points, say V, say some point here is say A, and some point here is B. So then VB minus VA will be equal to integral of this function, which is a function of x dx between A to B, or I should say, say I should write xa to xb. That's even clearer. So that's how you can actually calculate the difference by just, if you know the function here, you can calculate the change in the shear force between 2 points, and that will come in handy if you know Wx as a function, and not only like a constant, but it could be a triangular loading, that means linearly varying. It could be a parabolic loading in some cases, because it depends what situation you are in. And whatever be the function of Wx is, you can put in there and you can get the change in the shear force. Fine. Then what? Then if I want to calculate the variation of moment, what I would do is I'll just write the balance of moments. So what would be that, and then I'll just say take the moment about this point to get what say the positive is say counterclockwise maybe, so m plus delta m, what was there, then minus m, then what else is there, then v times delta x minus v times delta x. What else is there? Then this plus omega delta x times delta x by 2, right? So not omega, so this is plus w at x delta x by 2, I'll write not like this, wx delta x is the load, and the moment arm is delta x over 2, this goes to 0, right? Now what happens now? See, this is a second order term, because delta x and delta x both are small, so we can simply take it to 0, and here m gets cancelled. So what we are left with is say delta m is equal to v delta x. That means delta m over delta x is equal to v, and in the limit that delta x tends to 0, we have dm over dx is equal to v. So this is your relationship between the moment and the shear force. And exactly in the same way now, what we can do is the m at a location A, in fact it should be b minus m at A, the change between these 2 points will be the integral of v as a function of x dx between xa to xb, right? So that's the way to look at it. So that means if you know, that the function of weight which is coming as a function of x, by doing this you can calculate the function of Vx. If you put this as a 0 to x, you will get a function as a v as a x, function of x, and then that if you replace here, you will get again 0 to x, you will get m as x as a function of x again. So that's how you can calculate, which will save a lot of effort and time whenever you have a closed form function representing either the w or the v. And one more thing, see here. Now this tells you that wherever the shear force is 0, right? Wherever the shear force is 0, dm over dx is 0. That means what? the moment has to be maximum at that location, right? So what benefit it gives you is, if you have drawn the shear force and bending moment diagram the way we have done, say something like that, and wherever you see that the shear force is going through 0, so at the same location the bending moment has to be maximum. Okay, so here it is crossing, right? Though it's a jump. Okay, so the 0 point of shear force is somewhere here, so you are getting a maximum bending moment at this location, and that is the point where it's critical, because you are getting the maximum moment. So you know that the maximum moment will correspond to the maximum normal stress, the bending stress, and the failure possibility is higher there. So that's how you should interpret all these results, and this will help you in drawing the shear force bending moment easily, or even at least it can be used to check whether your shear force bending moment diagram that you have drawn by using the previous method is correct or wrong at every locations. So that's it about these relationships, and we will see you in the next segment for discussing about the deflection of a beam that as a whole. Okay, the deformation for calculating the strains we had discussed earlier, but now we will be discussing about the deflection of the beam as a whole in the coming segment. See you there.